In this lecture, I'm going to talk about what I think is one of the most important topics in spatial capture-recapture, and that is how do you use SCR models to describe spatial variation in density and test hypotheses about spatial variation. Of course, Chris touched on this a little bit when the sort of mode of spatial variation was among population variation. So if you do separate studies or sessions or sample grids in different landscapes and you want to test for variation among those, that can be covered in the multi-session models. But now we're interested in describing spatial variation in density over within a population, so over the landscape within which a single population resides. So there's kind of 6 subtopics to this lecture. First is, I think, the most important thing: how do you build in explicit models of density into an SCR model? Then we're going to talk a little bit about estimating the posterior distribution of an individual activity center. Of course, the point process model that describes how individuals are distributed on a landscape is one of the important elements of an SCR model. We view these point locations as latent variables or random effects. So they're unobserved, and naturally we might want to estimate the value of one of these latent variables. So that's an important and interesting topic. We'll talk a little bit then about estimating the expected number or density of uncaptured individuals, so that we could make a map of where those individuals exist in the vicinity of our sampling array. And then we'll make maps of realized and expected density, so we can depict where our population resides. And then we want to talk about a couple of maybe more or less minor topics, showing a map of the conditional probability of capture. And then that leads naturally to this thing called effective sample area, which, if you are familiar with distance sampling, you've seen similar quantities described for distance sampling models. And then the final topic, we want to talk about imposing state space constraints in the state space data frame object, although I think we talked a little bit about that yesterday. So yesterday we noted that one of the essential elements of spatial capture-recapture model is the point process model that describes how individuals or their home ranges are distributed on a landscape. The core assumption in oSCR is that the point process is a Poisson point process model. So what that means is that the number of points within the state space has a Poisson distribution. And this cap lambda here, this should probably be, I think, a cap D to be consistent with what how we expressed it yesterday. One implication of this Poisson point process assumption is that it implies for each pixel of the state space that the number of activity centers in that pixel also has a Poisson distribution, where then density can be expressed as a pixel specific value. So that's this second formula right here. So naturally then we can think about modeling covariates that are thought to influence density at the pixel level on this D of S parameter. We call this an inhomogeneous point process, where the local point density depends on measurable landscape or habitat covariates. And because D is a positive, has to have a positive value, we would probably use a log link to express the relationship between density at the pixel level and some measurable covariates. So in this log linear model for density, we have an additional parameter beta 1, which we're going to estimate by maximum likelihood. That's the effect of this landscape covariate on density. So I'm going to show how to do that here in a minute for the Fort Drum Bear data. One neat thing about R over the last few years is that there have been development of many R packages that allow you to do GIS operations within R. And so that's especially nice when you're using oSCR. We have a lot of spatial analysis capabilities in the oSCR package, like modeling landscape covariates on density, or as Chris mentioned in the previous lecture, cost functions for asymmetric space use models of detection probability. And one of those, so I think Dan worked up this example in one of the Smithsonian workshops a couple of years ago, showing how to just use the library SP and the library elevator to go out to the internet and grab an elevation map. It might be one of the variables that could affect things like density, or could be part of a cost surface that structures movement of individuals on a landscape. There are a lot of packages. I'm not really a good GIS person myself, but there are a lot of these packages in R that you can use to process spatial information, to create layers that could feed into oSCR either as part of the state space data frame or as a cost surface data frame object. So this specific example right here uses the SP library, and then I believe this must be a function in the elevator package to go out and grab a raster of elevation values for a specific landscape, which I think must be in the vicinity of the Smithsonian Mason School of Conservation building, where we've given this workshop for a few years. So you all should be able to just execute this code, although I think grabbing that elevation layer takes a minute or two. So if you execute it, it might hang up for a minute. But you can grab this elevation profile, you can plot it, and it shows the elevation layer in the vicinity of our workshop location, which I guess is that red X there. So that's one way you can use these R capabilities for GIS analysis to produce layers for modeling density or cost surfaces and so on and so forth. So I'm going to walk through, we're going to do an analysis of the Fort Drum Bear data. I introduced this a little bit yesterday, although I think in the context of the abbreviated lecture, it was a little bit without context. So I'll give a little more detail on the Fort Drum Bear data here. This is one of the data sets we have available in the oSCR package. So if you type data, bear data, the first line of our code here, you'll have access to the data objects that come with it. This was a study of black bears on the Fort Drum military installation in upstate New York. It's shown in the first map here. I think there were 38 barbed wire hair snares distributed around the southern part of the military base. And it was, in a lot of ways, just a standard non-invasive genetic study. These hair snags sampled hair from bears that visited bait stations. They were processed to determine individual identity using genetic markers, and then that produced a nice spatial capture-recapture data set that we're going to do some analysis of here. So the first few lines of code just extract certain element of the bear data that we're going to use in the subsequent analysis, processing and analysis here. So the number of individuals in the data set, the number of sample occasions, the number of traps, the trap locations. And I don't have the code here for making these plots, the study area on the left here, and then this buffered trap array is shown on the right. The sort of historical analyses of capture-recapture data, people would use this buffered trap array to compute covariates like distance to the edge, fit individual covariate models, and then make some attempt to convert population size to density using this buffered trap array. So again, the code for producing that is not shown here, but I think that's given in the SCR book. What we're going to do to demonstrate fitting of models for density is we're going to actually simulate a covariate. We didn't have a good density covariate for this Fort Drum Bear study, but what we're going to do is for the landscape in the vicinity of the trap array, we're going to just simulate some random numbers that look like a realistic spatial map that might describe something related to bear food. And we're going to fit models in oSCR that have that covariate affecting density. The first thing we do here is we're going to create our discrete state space of points. Chris showed how to do that with the make.ssdf function. What I'm going to show here is how to just create that grid with a couple of lines of R code. I define a buffer around, so the units of the trap coordinates are probably in kilometers. And so I'm going to define a buffer for this trap array to be in 4 units, which I think are kilometers. We're going to compute the longitude, latitude limits of the trap array, and then we're just going to add that buffer to those limits. And then we're going to create a grid of points in the X direction and the Y direction. In the X direction, there's 30 points between the lower limit and the upper limit. And then in the Y direction, there's 24 points between the lower limit and the upper limit. And the reason those are different numbers is because I want the grid cells to be about, I want the grid spacing to be about equal in the X and the Y direction, and it's not a perfectly square region. So that's a little bit sloppy because it's not exactly the same, but I think to illustrate what we're going to do here, it's just fine. Then to make the state space grid, I use the expand.grid function in R. I give it these list of coordinates for XG and YG, and it produces a nice state space grid. So for each of these state space points, you could imagine that if you were doing a study about things that affect bear density, you might do some remote sensing or some on-the-ground surveys to get a map of habitat or food resources for each of these state space points. And what I'm going to do on the next slide is just show you how to simulate something, save you a lot of field work. You won't have to do field work anymore. You can just simulate these excellent covariates of bear food resources. So the way we simulate this code, this is a little bit of a technical detail here, but we use this approach a lot, is we simulate landscape covariates as just spatially correlated random normal variables. I'm not going to describe why this is how it's done, but you just basically you need to define a variance covariance matrix that describes the strength of the correlation in this variable among neighboring pixels. And then there's a matrix algebra operation here where you take the Cholesky decomposition of that thing and you generate some random normal variables and multiply those things together. If you execute this code and then make a plot of the resulting simulated raster layer, then you'll see that looks like a nice patchy looking covariate that would make sense for, let me admit that person, that would make sense for anything that you might observe on a real landscape. So this is our simulated bear food variable. It shows areas of high bear food and areas of low bear food in yellow. And one thing I guess I need to point out is once we simulate this variable, which in practice you would have it by some GIS analysis and field sampling that you've done, the way this is attached to the state space data frame is just as another column. So I created the bear food state space data frame by taking our grid of points, so the X and Y values for each pixel of the state space, and then I just add another column, which is this this bear food covariate. So if you look at row 1 of this state space data frame, it has the X and Y coordinate, and then for each pixel some value of bear food. And then the plot, again, it looks like a reasonable landscape covariate should look. It looks patchy, reflecting the spatial correlation structure that we use to simulate the variable, but it's also how things usually look in practice. So once we have this bear food covariate, we've defined our state space, we have a bear food covariate, then we're ready to move on and create then the SCR frame. We'll have the two things we need to begin fitting models, the SCR frame and the state space data frame. On the first slide or the second slide of this lecture, we loaded the bear data. We're going to use data to oSCR to process the elements of that bear data list that is in the oSCR package. And then we're going to extract the SCR frame from what comes out of data to oSCR. So the call to data to oSCR is given right here, which you can execute. It uses the encounter data file, which is in the bear data, and it uses the trap deployment file, which is in the bear data. And as Chris showed in the previous lecture, we have to specify the ses.doc column, the ID column, the OCC column, occasion column, the trap column, and so on and so forth. And Chris showed a kind of a foolproof way to do that so that you don't mix those things up. Execute this, and it's going to produce an output file within which is this thing called SCR frame. So we create that SCR frame object called SF here simply by grabbing that element out of what is returned from data to oSCR. And then we have the state space object, which we create as a list using the thing that we produced 2 slides ago, bearfood.ssdf. Any questions about that so far? That's kind of processing that you've already seen, but just in a slightly different context. This is a single session data set, a single session study, but the operations are pretty much the same as what Chris showed earlier with his red-backed salamander data set. When we have those two objects, we're ready to fit a few models. You probably don't want to execute these because I think running all 6 of these models takes 20 minutes or more. But we've defined a set of models here where we allow bear food to affect density or not, and then we allow the other parameters P0 and sigma to be sex specific. So that defines 6 models, beginning with a constant model. It's constant for all parameters, and then working up to a model where both parameters, both detection parameters are sex specific, and we have bear food in the density model. So again, 6 models, if you run that, it takes 20 minutes or even a half hour to run all of them. I should have put the output up on the Slack channel. So we'll add that after the lecture here. When we fit all of those models, we again want to usually do some kind of model selection or produce a summary table of how the models all fare against each other, so we can use the fit list function in oSCR to package up all of the model fits, we can create then a model selection table in the same way as Chris showed earlier. And again, the difference is this isn't a model, a multi-session problem. It's just one session, but the models vary in what covariates are on the different parameters. When we do that, the mod cell function produces a table where the models are ranked by AIC. And what we see here is that the model where bare food affects density and both of the detection parameters are sex specific is the top model. It's 4 AIC units better than the next model, has about 88% of the AIC weight. So we might feel confident just summarizing and reporting results for that one model, although the model without bare food on density also receives a fair amount of AIC weight. So our summary from this might be that bare food seems to be really important for bears. It's the top model receiving close to 90% of the AIC weight. And this you might intuit this even before fitting a bunch of models in oSCR, because this plot shows the average capture location for the 47 bears that were captured in this study superimposed on this bare food covariate. And we do see kind of an average, we see probably a pattern here that we might start thinking, well, maybe there's an association between where these bears are located and this landscape covariate that we collected in our study that actually was just simulated. So maybe it's a little peculiar that there's such a nice association, but that's what it sort of looks like just by looking at this plot. And I have a homework question for people to think about. If you didn't know anything at all about spatial capture-recapture, but you just looked at how the average capture location was distributed across this landscape, you might think about answering the question, is bare food important, by simply doing some kind of a regression of these locations on the bare food covariate, or binning up the landscape, counting up the number of locations within each bin and doing a generalized linear model. And so the homework question to think about is why not just do that regression to answer this ecological question? What would be wrong with just doing some kind of a regression of those red S locations on this landscape covariate? So that'll be something that at the end, maybe people think about that as I go along here, and we can have, I hope, a little bit of a discussion about that at the end. So so we fitted these models. So we packaged up our data. We fitted these models. We have a nice map of this covariate with the data superimposed that suggests it's probably important. The AIC supports that it's important. Let's look at summaries of the models that we fitted and then try to interpret the results from those model fits. Model 6 in the object called OUT6 was the most important model by AIC. This is the model that has sex structure in both the baseline and counter probability parameter, as well as the space use parameter sigma, and it also has bare food in the density model. If you look down here at the parameter estimates, you see again, these are on a logit scale for P naught, the log scale for sigma, and the log scale for density. What we see, intercept maybe isn't that interesting to try to interpret, but we see that the P naught for males is a negative value, which suggests actually that the baseline detection probability for males is lower than it is for females. If we look at the sigma parameter, we see that the effect for for males is actually very positive, suggesting that the value that the space use parameter sigma is actually quite a bit larger for males than females. So I think taken together, these results probably suggest that males are using more space than females, but maybe they're using that space less intensively. So they have think about a utilization distribution that's kind of squashed down and spread out a bit. I think that's the interpretation of those two results there. And then the important result, the important ecological result here is the effect of this bare food covariate on density. And we see here that it's a very positive value, 0.659. And it looks to be, just using basic statistical principles, you would call that a significant effect. And I think that's sort of the big result. We find that bare food seems to have a positive effect on the density of bears on this landscape. Are there any questions about those results?
Andy, it might be important to point out that it is somewhat troubling that our simulated covariate was shown to be important, but that's kind of why we included it, right?
Yeah. Yeah, so we used to not tell people that this was a simulated covariate so it made sense. We're like, oh, we collected bear food and it's important. But yeah, so we simulated this, and so to be honest, it was simulated. I did the simulation 5 years ago, and I simulated a whole bunch of bear food covariates until I found one that was significant, and this is the one that we simulate here. So you see, I set the random number seed up here. This is a random number seed that produces a bear food covariate that's important, so that you would think that this might be one that you collect in a study that you're doing of bears or whatever your species is. So so that's the story behind the bear food covariate. We didn't have a covariate for the Fort Drum study, so we had to invent one. But yeah, so interpreting these parameter estimates, this is a table. A summary of this might appear in a paper or report that you write about your study, along with some narrative interpretation of these estimated parameters. In addition, you might include a model selection table, like we showed on the previous slide. So here's I guess I'm not sure I have anything to say about this model, but here's a simpler model with just the bear food covariate and no sex structure on the parameters, just kind of by way to contrast with the top fitting model. It shows the important bear food effect, but it also shows about 11 AIC points different between the top model, really emphasizing that we need that sex specificity in the model. And that, I think, typically happens for most carnivores. You find some sex structure in those two detection model parameters to be important.
Andy?
Yeah.
There was a question about TRIM-S.
Okay, yeah, so the TRIM-S basically speeds up the likelihood evaluation by doing a local evaluation of the likelihood. So around, what it does is it takes each encounter history and computing the likelihood, just looks at the part of the state space in the vicinity of that encounter history. So the TRIM-S sort of defines how local that evaluation is supposed to be. So we use that in a lot of model fitting that would take a long time, and it speeds things up a bit. You need to be a little bit careful. There's probably some discussion of this in the help file, but you don't want that to be too small, because then you're actually truncating the likelihood and you're not going to get the true MLEs. So you want that to be a little small enough to improve the computation, but not too small to affect the results. and you probably have to play around with it a little bit to really have a good sense for whether things are okay there. I think that's all I want to say about that now, but we'll be glad to discuss more about the trim-S in the Slack channel, and also I'm pretty sure it's probably discussed in the oSCR.fit help file.
And then one last thing, Andy, there's the psi constant parameter.
Oh yeah, okay. So as Chris described yesterday, the sex structured likelihood is kind of a feature of oSCR, and the parameter that allows us that describes the sex distribution in the population is this psi.constant parameter. It's the logit scale probability that an individual in the population is a male. So if you take the inverse logit transform of this value, that's the population probability that an individual is a male. So somebody take the inverse logit of that and tell me what the value is. It's probably like 0.35 or something, I'm going to say. So there's like the probability that an individual is a male is around 0.35 or something like that. So whenever you have the variable sex in your SCR frame, there's going to be a psi.constant parameter in the model output, because oSCR will fit this sex structured model. So even if you don't have sex structure in the parameters like model 2 here, we have no sex structure in the parameters, but because sex is in the SCR frame, by default, oSCR is fitting that sex structured model. And the reason that's done by default, even though there's no sex structure in the parameters, is then we can compare these AIC values between models with and without sex structure. So this AIC value is comparable to this AIC value, or even though this model doesn't have any sex structure. If you weren't fitting the sex structured likelihood, so in other words, if the sex data weren't being used to estimate this parameter, then those AIC values would not be comparable, because one of the likelihoods is missing a chunk for the sex data. We described that in the paper that Chris cited yesterday, that describes this multi-session sex structured likelihood.
Yeah, I'll add to that, Andy. If you have no sex in the model and all individuals are known sex, then that parameter is just the ratio of males and females in your data. But as you start introducing unknown sex, then, and also add sex-specific detection parameters, you can end up with the ratios different to the ratio observed in your model.
Yes, that's a good point. So this value here, if you take the inverse logit transform of that, it should be it should be consistent then with the sex, the frequency of males, relative frequency of males in the data set. So I probably should have checked that before we got into this discussion, but I'm pretty sure it probably is consistent with that. But you see that this value changes in the model where we add sex structure to some of the parameters. And the reason that is because as soon as you add sex structures to some of these parameters, it implies that males and females are detected at different rates. And so what that does is it then adjusts the population estimate of the probability of males from the sample estimate. So when there's sex affecting detection model parameters, that means males and females are appearing in our capture-recapture data set at different rates. Okay, what I want to talk about now is estimating these individual point locations. So things that we called, I think, activity centers or home range centers yesterday. These in the SCR model, these are latent variables, so we don't observe them. We have to put a distribution on them. That's the point process model. And then they're not estimated as explicit parameters of the model by maximum likelihood, but rather as a technical matter, we wind up removing them from the likelihood by integration. That's what's happening in the oSCR.fit function. But what we can do after we obtain the MLEs of the structural parameters of the model is we can get an estimate of each of these latent variables using Bayes' rule. So we can basically compute the probability distribution of any given activity center S given the data for that individual, and it's just proportional to the conditional likelihood of an individual's encounter history given its activity center, and then multiplied with the prior distribution for this random variable S, which is the point process model. So with that expression in mind, we can obtain the MLEs of the structural parameters of the model, P naught, sigma, density parameters. We can plug it into this Bayes' rule formula, and we can get this probability distribution for any given S, given the encounter history for that individual. We have a handy function called predict.oSCR that if you give it the fit object in the state space data frame, it's going to produce these estimated distributions, these estimated posterior distributions for each individual activity center. It's going to produce them for all individuals in your data set. And then it's also going to produce that for an uncaptured individual. So there are individuals in your population that have the all zero encounter history. Those are uncaptured individuals. And so the predict.oSCR function is also going to produce an estimate of this posterior distribution for that all zero encounter history. I was looking at this predict.oSCR help page last night, and there's a couple of syntax errors as we developed oSCR a little bit that cause an error. So I'm going to push an update to that help file sometime in the next couple of days so that it runs cleanly. Mostly what we're going to show in the following bits of code is more or less mirrored in that help file, but with the errors fixed. So I'm going to show now how to use this predict.oSCR function to produce this estimated posterior distribution for a given individual's activity center. So the first line of this code, which you can execute, I think it runs pretty rapidly. So if you wound up running those model fits given previously, they might be finished now, and you could execute this predict.oSCR function. Feed in the model, the fit object that you're interested in generating predictions for. It requires then the SCR frame and the SS data frame. I have an argument invoked here called override trim. And basically, if you fitted the models using the trim function to use the truncated likelihood, then the predict function won't generate predictions for the whole state space. If you wanted to generate predictions for the whole state space, you need to say override trim equals true. So that's the reason that option is in there. So what I'm going to, once you execute that function, it generates a list with a whole bunch of stuff in it, okay? And the thing that we care about, if you look down a couple of lines, this object called pred here has one list in it called PREDS. Those are the predictions for each of the activity centers. So there's a whole bunch of other stuff in here, but the thing we care about are the predictions. And it's going to be a list consistent with our multi-session structure. There's one element of this list for every session in the study, because the Fort Drum data set is only a single session example. There's only one element to this list. So PREDS, and then accessing, referencing the first element there just pulls out one big matrix, which has a row for every single individual that was captured, and then one additional row, which is the row that corresponds to the all zero encounter history. So this whole block of code right here is grabbing the matrix for session 1, which is the only session in the study, and then it's grabbing a specific row of this matrix, which goes for individual 40 in this data set. So there were 47 individuals captured, and just for whatever reason, we decided to illustrate this posterior distribution estimation for individual 40. So we execute predict.oscar, we get this this vector of posterior predictions, which is going to have, so it's a long vector, and it's going to have a value for every single pixel of the state space. So that's, I think in this case, 720 values. So the state space has 720 pixels. There's going to be 720 values of these a posterior probability for this activity center for the 40th individual. The rest of this block of code here, so this uses what I think is one of the most useful functions in R. It's from the raster package. It's raster from XYZ, which takes a matrix of X and Y coordinates, and then some variable Z, which you want to make a spatial map of. So in this case, I C-bind together the X and Y values of the state space pixels, and then I add to that the pixel specific values that are these posterior probabilities. So I'm plotting the raster that raster from XYZ function produces. I'm going to add then the trap locations to that map, and that figure is shown at the bottom of the slide here. It shows the estimated posterior distribution of the activity center for individual 40, and it also shows the rest of this last 3 lines of this code plots the traps that individual was captured in. This individual 40 looks like was only captured in one trap, and it's shown there with, there's a red 1 over that trap. That individual was captured one time at that trap right there. And after estimating the model parameters and then generating a prediction of this individual's posterior distribution, it shows a high likelihood that the green pixels and yellow pixels are high probabilities of containing that individual's activity center, and the orange and the white colored pixels have low probability of containing that individual's activity center. So what this is, it's a probability distribution for where that bear lives. If you could imagine being interested in that, you might not be interested in it for a particular bear or whatever, but we're going to show something nifty that we can do with these estimated posterior distributions here in a minute. Okay, so kind of a related topic here is something that you can do with the predictions that come out of predict.oscar is you can produce a map of the density of uncaptured individuals in your population. So you know, of course, what we estimate this parameter D, which is the density for the population, and what when we have a trap array that is not completely covering a state space and it's irregular trap spacing, we wind up their individuals within the population have differential probabilities of capture. And so individuals that are exposed to a lot of traps are more likely to appear in our data set than individuals that are located far away from traps. And it's I think, informative in some cases, possibly as a measure of efficacy of your trapping array, to look at how the distribution of uncaptured individuals is distributed. And so what we can do is we can take the very last row out of that predictions matrix, and that is the expected number of uncaptured individuals. We can make a similar raster plot of that vector. And that's what this map shows right here for the Fort Drum Bear data. It shows, I didn't put the trap locations over this image, but where all this white is, that's of course the trapping array, the hair snag array, and the model suggests that there are very few or no uncaptured bears that have activity centers on the interior of that trap array. And as you move away from the trap array, remember the buffering here was 4 kilometers. So out here, I wonder if that's 4. I guess that might be 4. If I had put the trap array, you would see that. But as you move away from the trap array, the model then thinks that there are probably some bears out there that were uncaptured. So, you know, as the color goes from white to yellow to orange to green, the expected number of activity centers in a given pixel increases. And so the model, for whatever reason, thinks that there may be a few more bears out in this southeast corner of the state space than elsewhere. If you look at the bear food map, the bear food map shows really good bear food down here, right? Really good bear food, but no traps. And so the model takes that, because we're generating a prediction for the model that has bear food as a density covariate. The model says, well, you know, there's a strong positive effect of bear food on density. There must be some bears that we're missing down here. Anyway, this is a cool plot that it sort of shows within the state space that encloses your study area where are you not sampling well. That's really what this is all about, is where are you doing a good job sampling, where are you not doing a good job sampling. Okay, so these maps that I just showed, the estimated posterior distributions of individual activity centers, the expected number of uncaptured individuals, those are cool maps to look at. But one of the things we can do with those is we can actually produce a density map of the population. So we can take all of those 47 posterior distributions, we can add them up, and then we can add to that total the contribution of uncaptured individuals, and that's a spatial map of the population distribution. We call that the realized density map. And so if you just take all of those two maps we just showed, this map and this map, but there's 47 of these maps. You add all of those things up, you can get this density map, which is a really cool thing to look at. And people are, in fact, I think, interested in this in a lot of population studies. So let's see, to produce that map from the output of the predict.OSCR function, you just grab this element called R. Okay, that's the realized density for session 1. You could sum up those bits longhand, but it comes as part of the output from predict.oscar. You can take this, this R, which is already a raster, I guess. If you just plot that thing, it shows the realized density map here. And it shows, again, the units of this are bears per pixel. A pixel is a little less than a square kilometer in this case. But it shows very clearly areas of high and low density corresponding to sort of the combination of this landscape covariate bear food and the realized pattern of bear detections. It merges those things together and produces a map of density. And the reason this map is useful, I think, I mean, ecologists probably, if you're studying bears here or some species somewhere else, you probably have a good intuition as to what's affecting population density and so forth. But I think from a management standpoint, these maps, these density maps are useful because it allows people to partition the population up into maybe management units or conservation areas or something like that. You can take this map, you can partition the density however you can draw lines on the map. So that's, I think, one of the most useful things that you can do with this realized density map. The map on the right shows the same thing, but again with the superimposed, the spider plot that we've shown many times. So where are the captures of individuals? How are those of the same individual connected, and so on and so forth. So again, this realized density map is just a sum of these two pieces, the estimated posterior distributions for every single individual that was in our data set, and then a contribution for the uncaptured individuals in the population. That's what we call realized density. The other thing we can compute from the output of an OSCR fit is we can produce what we'll call an expected density map. Expected density is different from the realized density. The expected density is the estimated density under the assumed parametric model for, in this case, density. So we have an assumed model that says density varies in relation to bear food. And so when we can evaluate that density model using the parameter estimates from the fit, and we can produce a plot of that. It's called the expected density instead of the realized density. The realized density takes into account the actual capture locations of the individuals. So to produce the expected density map, we can use the get.real function, which Chris showed some examples of earlier this morning. This produces, for the model where we have a density covariate, it produces a prediction for every single state space pixel, and also, because it's a sex structured model, for both males and for females. So if you run this, this command at the top of the page using get.real, I think it's going to have, so there's 720 pixels. It's going to have 1,440 rows in that, I think, in the output file. So for both, for each sex, male and female, it's going to have 720 pixel specific values. So you can then subset that output, and you can produce a density map for both males and for females. And I don't think so it looks like here, okay, this is just so this isn't broken down by, the plots aren't broken down by male and female here. This is the expected density of both males and females together, and then that's shown in comparison to the realized density map, which we showed on the previous page. But what you could do is you could take then just the male and female expected densities, and you could make plots of those and possibly observe differences in how males and females are distributed in the population. Okay, next to last topic here is we want to talk a little bit about what I called here conditional probability of capture and then expected sample area. Another thing that you can produce a summary of from the predict.OSCR function is spatial variation in probability of detection. So you can ask the question, what's the probability that I captured an individual at all, given that its activity center is located in a particular pixel? And this expression at the top of the page, this just follows from the binomial encounter assumption of the basic SCR model. There's different assumptions here, but you can fit the model, you can get parameter estimates for this detection probability function, and this is just a formula that you evaluate. And you can compute this probability of capture of an individual during a study for every single pixel on the landscape, and that produces a cool looking map. Again, it's kind of looks a lot like that map of the frequency of uncaptured individuals that I showed before. But one thing that we do with this conditional probability of capture is we can compute the expected total probability of capture of an individual, this thing we called P star before. And this is a nice quantity to have because it gives you a measure, in a sense, of the design efficacy. You can think about designing studies that give you a really high value of this P star. Gates is going to talk about that a little bit tomorrow. But it's a good summary of your design for a given landscape, for a given state space. How high of a fraction of the population do we expect to capture? One thing, another sort of analogous quantity that we can compute is what we'll call the expected or the effective sample area. And that's really just an area weighted average of this conditional probability of capture. So if all of the cells have equal area and it's 1, it's just really the sum of these conditional probabilities of capture. So this is a thing, again, people use this in distance sampling to talk about effective transect width and things like that. This is in the output from the predict.OSCR function. It's called P bar. And again, it's a list because in a multi-session situation, there's going to be a given P bar map for every session. So you can grab this P bar element out of there, and you can, I guess it's already a raster, so if you just plot it, then it shows up like a nice sort of visual description of your system. And then the second set of R commands on this slide show the calculation of the effective sample area. I think the pixels that I created for that state space, I hope they're 0.89 kilometers on a side. So the area of each pixel is that squared. And then we can compute the expected or effective sample area by just weighting those probability of those conditional probabilities of encounter by those pixel areas. And actually, I think this is confusing now that I look at it. I call that P bar. I guess that, so this quantity, this conditional probability of capture is actually called P bar. So I think I hadn't used the P bar before in reference to that. And so I think I should change that. But this P bar is that conditional probability of encounter. So it has a value for every pixel on the landscape. So the interpretation of this figure is, I guess it's pretty obvious. We're where we get into the interior of the trap array here, where it's dark green, the probability of encounter of an individual that would have an activity center at one of those dark green pixels is really close to 1. I mean, it's higher than 0.9. And then as you move out to the periphery of the trap array and even out into the corners of the state space, the probability of encountering an individual at all is getting very close to 0. Okay, the very last topic related to modeling spatial variation in density is this topic of imposing constraints on the state space. And I mentioned this just briefly yesterday too, but in a lot of real studies, we have restrictions that are on the state space that are really important. So if we have study in a coastal area, there's going to be a lot of water, bays, lakes, oceans that might not be suitable habitat for species that we're studying. If we're doing a camera trapping study in a park unit that's on the edge of a city, we might not want to include really urbanized areas in our state space. So really, we want to be able to impose these kinds of constraints that are really imposing constraints on a density model. We're making an assessment that density is 0 over some regions of this landscape that we're studying. And the way we deal with that in oSCR is because we're using a discrete state space, we just clip out points that are in these regions that we deem to be not suitable habitat. So the wolverine example that I talked briefly about yesterday is on the coast of Alaska, and there's vast areas of the sound that we want to be able to clip, a basin sound that we want to be able to clip out of the state space. So we create this state space object, and we use GIS operations, or just by pointing and clicking a mouse, we remove these state space points that are not, should not be part of the state space or candidate locations of the activity centers. So that's something that happens in a lot of studies. It's a way of effectively imposing a model for density. The other thing that we can do to deal with these, restrictions that aren't this profound is we could model a covariate effect. So certainly if things are more, if the landscape has more of a gradient that might affect density, we would put that in as a covariate. So we might have urbanization as a metric covariate that we put in the density model. Or as I said here, we could use, we could account for a very heterogeneous landscape by using this asymmetric space use model that Chris briefly mentioned earlier this morning. So that's the very last topic on dealing with spatial variation in density. A couple of summary points here. First of these, I think, would be obvious to anybody that understanding spatial variation in abundance or density is a fundamental objective in many ecological studies. As ecologists, we care about this for populations that we study. And secondly, SCR models allow testing hypotheses about variation in density from encounter history data. And this is one of those things that I think is really profoundly different between SCR models and ordinary closed capture-recapture models. They allow no formal inference about how the population is distributed over the area that you deployed traps. So that's all I have on modeling variation in density.